special talk. So this will be delivered by a very distinguished and senior scientist from the Chennai Mathematical Institute, Professor H.S. Mani. So before I request him to speak, I would like to say that we have been conducting these kind of online talks since October 2023, almost every Sunday, with the intention of informing our members and students about a variety of new topics in an informal way, all the way from quarks to cosmology. We have been doing that, and the response has been very good. And several faculty members from colleges, universities, and institutes have contributed their mite in making this program very successful. And we have also, as you know, held talks in Kannada, the local medium, with the intention of encouraging this at the higher education level, for the sake of proper communication between teachers and students. We all know the difficulties faced by students. So therefore, we thought gradually we have to introduce the local language at the higher education also. So we have been making some effort in that direction also. And today we have the distinguished Professor H.S. Mani, who is going to talk about some interesting problems in physics, fun problems. So before he begins his talk, I request Professor Usha Devi, who knows him very well, to give a brief account of Professor H.S. Mani. Over to Professor
Thank
Usha
you.
Devi.
Thank you. Okay. I hope I'm audible.
Yes, yes, yes.
Good morning, everybody. It's my pleasure to introduce today's distinguished speaker, Professor H.S. Mani, who is adjunct professor at the Chennai Mathematical Institute, Chennai. Professor Mani, is a renowned physicist with deep passion for both research and teaching. And over the years, he has contributed significantly to the field of theoretical physics, high energy physics, with particular interest in areas such as condensed matter physics, quantum mechanics, statistical physics, and his taste for teaching pedagogy is something which highly impresses me, and I keep him as a model for all of us who want to communicate and teach students. He has been associated with several prestigious institutions. He was the director of the then Mehta Research Institute, which is now called Harishchandra Research Institute, and his academic journey is kind of a testament to his commitment to the advancement of scientific knowledge. And he has been an inspiring educator, as we know. And we are fortunate to have him here to share his insights and perspectives on fun problems in physics. And this talk promises to be an exciting and engaging session where Professor Mani will explore some fascinating problems that he had posed to his students at CMI. And these are not only intellectually stimulating but also provide us with deeper insights into the wonders of the physical world. And we look forward to a wonderful session. And without further ado, I would like to hand over the stage to Professor H.S. Mani. Please join me in welcoming him. Thank you.
Yeah. Please, you may start, Professor Mani.
Thank you, Usha, and thank you, Kagali, for this invitation. I really enjoy communicating with teachers, and that's, I think, the right way we have to proceed to improve our educational system, especially in physics, which is already undergoing in many places, and Karnataka is one of the leaders of this. So it's great pleasure and a privilege for me to be able to talk to you people. So let me start. This is a course I gave last semester on classical mechanics. So every second week or so, I would spend 10 minutes of what I called fun problems. They were counterintuitive to what we think. And what is theory and what actually happens are two different things. So let me now go to here. Let me ask this question. Now, on a day which is the solar equinox, March 23rd and September 21st, every year it happens. One more thing, at the end of every problem that I discuss, I would wait for a few minutes, and if there are hands raised, I would like to discuss that with them. they may have some interesting comments to make, which I would like them to share with all of us. So let me now proceed. As I mentioned, there are 2 times, March 23rd and September 21st, when we have 12 hours of day and 12 hours of night. If you look at the website online, you will find that it is not 12 hours, but 12 hours and 5 minutes. Where does the discrepancy come from? I've already answered it here. It comes because of the refraction of sun's rays as they pass through the Earth's atmosphere. The difference in daytime is split equally between the morning. The sun is above the horizon and remains above the horizon, and the sun sets below the horizon. The refraction causes the sunlight to appear slightly early in the morning and remain later in the evening. Now I have to do one more thing here. Where is that figure? Now you can see this here. Usha Devi, is this clear? Can you see the picture?
Yeah, we can
Yes,
see.
yes, we can see it.
Okay, now you see the sun is below the horizon, still it is visible to the eye because of the refracted rays coming through this. In fact, we have to model the density of air, because then the refractive index is sort of, you make an assumption and see how the ray tracing takes place. That will give you the time in which the sun will be visible. This is tabulated all over various towns in India and abroad. And this is one way of trying to model the density of air as a function of the height from the surface of the Earth. It's a very important way of doing it. Okay, now let me go to the next one. Here. Now we know, let me just wait for half a minute or so to see if there are some comments on the first one which I have mentioned.
How can we calculate it to be exactly 5 minutes delay?
It is not exactly 5 minutes. If you go very carefully, it varies. It varies from 4 minutes 45 seconds to 5 minutes 15 seconds and so on. It's not, because the atmosphere density of air is very local, right? If there is a factory nearby, it will change, and if there is rain, it will change. So those things we cannot take into account now.
So therefore, the delay, the difference should vary from place to place, sir. So because the atmospheric conditions will be different at different places.
Correct.
Is that correct?
Yes. As I understand it, is correct. Incidentally, I also, this I did just for the equinoxes. You can calculate the sunrise and sunset time for the entire year, and that's also tabulated in the net. You can see that. That calculation involves some spherical trigonometry, but physics of it remains the same.
Thank you. Thank you.
It's average calculated over the entire year, sir. Is it?
I am willing to share that those slides for anybody who is interested, because that involves also certain other concepts in astronomy, which is there, which you have to worry about. The ecliptic, the celestial sphere, and the way there is a time at Greenwich time, how do you have to account for it, and so on. Shall I now proceed to the next one?
Please proceed to the next one.
Okay, we now proceed to the next one. Now, we know one thing. The moon is orbiting around the Earth in an elliptical orbit with an average distance of about 3, whatever figure I have written down, maybe very close. And this is primarily due to the gravitational force here. The Earth is also moving around the sun. So, how do you expect the moon's orbit as we go around the sun? Our first reaction would be to say the moon orbit will be some kind of a figure which will circle the sun, but that's not quite right. The figure looks like this. Notice the origin is the sun, and here, can you see with the cursor?
Yes, we can see.
Yes?
Yes, we can.
Okay, very good. Now notice the curvature is always concave towards the sun. It never is like this.
Ah.
When the earth is going around, it is never like that. And we can calculate this very easily just from high school mathematics. Let's just do that. We know the force mass Earth is given by the standard gravitation Newton's formula. All these are there. You can evaluate this, and you can evaluate the moon's one from sun and moon's one from Earth. In spite of the fact the moon sun distance is much larger than the moon Earth distance, because the mass of the sun is much larger, the force exerted by the sun on moon is larger than the force exerted by Earth on moon. So it means the force due to the sun dominates all the time, which means the acceleration should always be pointing towards the sun and never towards the Earth. So that's why it makes it concave. Yeah, I've written down comparing the two forces. It works out to be about half force of moon, Earth. The force of Earth on moon, force of sun on moon is about half. You can do this calculation. I'm sure even a high school class 12 student should be able to follow this art. And he can be asked to draw this using some software. I have done it using mathematics. So, is there any question?
The orbit of moon
Yes.
with respect to sun is drawn, and there are variations.
Yes.
The orbit
That's
of
correct. That
moon,
variation is because the force due to Earth on moon keeps changing the angle, right? So you have to add
right,
it
right.
accordingly.
Yeah, but if we look at moon's orbit with respect to Earth, will it show any difference?
It is like this. The moon's orbit with respect to the sun is what
Yes,
moon
yes.
shows.
But moon's orbit about around Earth, that doesn't show
Around the Earth will
any.
be more interesting. Yes, you are right. I have to learn to plot that also. Good idea.
Okay,
I should plot it side by side.
right.
Then you can see the difference. Thank you. That's a good
Okay,
idea. I will do that. Okay. This
Professor Mani,
yes.
Please ask.
yeah, somewhere when we use this force law, should we not use both ms plus me somewhere when we calculate the period?
I cannot use what?
Some of the masses.
Why, Malesh?
I mean, while applying Kepler's third law, this t square by a cube is given by 4 pi square by gm, but that m happens to be sum of the both.
No. Are you talking about the center of mass problem?
Yeah. So then, I mean,
It doesn't matter.
is it moon's mass very negligible that way?
Yeah, definitely. Definitely much more.
Yeah, right.
Will not
I
be-
was wrongly thinking about Earth mass. Thank you, sir.
Definitely
Actually,
much more.
we plotted it exactly for the entire case vectorially. And there are diagrams in the web which I have not seen. Very good. I think that also should be mentioned. The fact that the center of mass, because the center of mass between Earth and moon motion will be more different than for the case of moon with sun. Sun being heavier, it will almost be the sun. Okay,
Thank you, sir.
Malesh, you are the person from Mysore?
Yes, sir. Very
Hello,
much.
how are you?
So nice.
Nice to
Please
see you.
continue.
It's a long time I heard you. Okay. So now I will go to the next problem, which is actually from Maureen's book. It's not a very difficult problem, but still for students it will be. Supposing you are inside a gas balloon fixed to the earth. Give a reasonable definition of which way is down. It's plumb line, which gives it. This is not a very difficult question, but still, I thought the student should be able to answer this question. And no. So I will proceed to next few interesting questions. All of us know that children play gulli danda. The names may be different in different parts of India. In north there is gulli danda. I do not know what is it in Kannada.
Here we call gilli dando. Gilli dando.
Gilli nadu, is it?
Gilli dando.
Gilli dandu.
Yes.
Okay. In Tamil it is called kitimbul. I don't know what is it called in Malayalam and Telugu or Bangla. Anyway, so the question is this. We hit the gulli with the danda, but we are hitting it downwards. If you are hitting it downwards, how can the gulli move upwards considerably? The answer is immediately we'll be saying the reaction from the ground. But then we have to realize, why is the reaction from the ground more than the force I'm hitting it downwards? How can the reaction of the ground be more? We have normally never seen this happen. So I will explain how it happens. I have drawn a model of a gulli. This place BC is the one which is touching the ground, and the impulse by a person is given here. When it is given here, the gulli will turn in that direction because there is a torque acting.
Torque applied, yeah.
Is this clear?
Yes.
Gulli,
Yes.
A, B, C, D, G, H is the gulli, and CM is the center of mass, and the force impulse F is given here. If it is given here, the gulli will turn like this. When it turns like this, it will be C, about which it will turn. The normal reaction will be here. So now you will have to calculate how much is the normal reaction. How would you do that? You do this by saying N times OC. Okay. Whenever we calculate the use Newton's law or torque, we have to always work with the center of mass. So I am taking N times OC is equal to F times OD or OX. OX is larger than OC. So if X is larger than OC, then N must be larger than F. So if N is larger than F, it will move. I will wait here for a few minutes or 1 minute.
So this gulli would jump up and also turn both at the same time, sir.
Pardon?
It is going to turn as well as push up.
Yes,
Jump
it will
up.
go up.
Both phenomena will be there together.
Right.
Rotational motion and linear motion also.
Yeah. The calculation has to be a little bit more detailed, which I have not done. I have assumed at time t equal to 0, the angular momentum or angular acceleration is 0. But there will be some angular acceleration which I have to worry about, but those calculations are a little bit more detailed. The broad explanation is what I've just said. Okay.
Oh, I mean, isn't the reaction force equal to the action force? Are we violating third law?
No, I am assuming that when this thing has hit, the angular acceleration of this is 0. It is not completely right. There is angular acceleration, but that's because this is small, the angular acceleration will be very small.
Yeah, I will have to think about it. Thank
That's
you.
why
Please
there is an
continue.
impulse here. there will be an impulse there. But that impulse is very small. Most of the effect is it is trying to go up. Okay, let me just give you another case here. Here, I'll just go here. Notice, supposing I design my gulli danda this way, and I give the impulse here. If I give the impulse here, it will rotate about x, but this distance is larger, so it will never take off the ground. So people never make the gulli like this, they always make the gulli like this.
Yes, correct.
Okay, one can think of, in fact, this could be a good problem for an undergraduate to design a very good gulli so that it can rise very high, so that the person who is hitting it has enough time to hit it properly. One can design
We can tape. If the tapering is more sharper, right, like GD or CD very long,
Yes.
will it help?
Yeah, I don't know. I'm not sure. See, these days with mobile phones, one can take pictures and see exactly what is happening.
And also, if one takes this as a, say, a symmetric rigid body or something, and then calculate it exactly, it may be difficult. I don't know, but
Please say that again.
that is the Euler equations. That is to take either whether this is a symmetric rigid body, and then I have a applied force and use Euler's equations with torque. So it may be difficult to solve in that case. I don't know. So,
Yes, I agree.
but it is only that is a simplistic kind of a explanation which will give us some general idea, if not fully.
Yes, yes.
Okay.
Anyway, I think if there is a possibility of a small project for a student who is in first year or something in a class who is interested in doing it, there is enough thing which can be explored.
And also, sir, one more thing. The top surface, the AHHD, the top half of the gilly can be flat also. It need not be curved. So it can be flat. One half can be flat. Only the other half could be designed like this in a curved manner.
Sure.
So that will it help? Or will it be better? I'm just imagining.
One could even think of various things, semicircles.
Yes.
2 arcs. Okay, now this is a very, very interesting problem, but it has some reason for it being done. Unfortunately, rather a sad incident. In 1964, Kennedy was assassinated. When he was assassinated, there was a assassin fired a bullet from the back. It went through his head. When it went through his head, the head moved backwards, did not move forward. So when the case came to the court, people said, you have caught the wrong person. Some lawyers saying that the criminal must have been in front of Kennedy and not at the back. So this went on for some time till the judge decided to consult a physicist. And the physicist was a very famous one called Alvarez. And here is what happens. Here is the bullet. I have just taken this. Can this be seen in the screen?
Yeah, you can see.
The bullet is going forward. This is over a melon. When the bullet is going forward, these things go forward, but this big piece will move backwards. This is completely counterintuitive. And let us see why this happens. See, the melon is not a rigid body. Our human being is not a rigid body. So here I will share the reference of Alvarez with you. He writes it very beautifully. I think all of you should try to read the article by Alvarez. Okay. And of course, he goes into great detail about analyzing the photograph when Kennedy was assassinated. Okay, now let me just use this. Let m be the mass of the bullet. I want to do it rather slowly because this is a very interesting problem. And mm is the mass of the melon. Let Vb and Vm be the velocities of the bullet in the melon. Before collision, the bullet is moving at the velocity v and the melon is at rest. Assume that the bullet stops inside the melon. It need not, but then the calculation becomes easier. The more realistic case can be dealt with similarly, and I leave it to you people to fill up the details if you're interested. The first equation is just mv vb is equal to mmvm, conservation of momentum, and the next equation is cancelled. Now, if you do this, if you calculate it, only a fraction of the bullet energy is transferred to the melon. The rest of it actually goes to the fluid part of the melon. Of course, some of it is also converted to heat, which we assume it to be small. So let us do a small numerical calculation. Numerical calculation is here. Let the mass of the bullet be 10 to the minus 3, 1,000th of the melon mass. So in the above equation, from that first equation, this constant f can be calculated and m is given by that. So now momentum here is 2 mf tf. Tf is the kinetic energy. I will halt here for a minute just to see if there is any question on notation or whatever I've done.
What is PF, sir? PF is PF stands for
Yeah.
Kinetic energy.
PF of PF.
Yes. I think I must have written there. No, not written.
No.
You got MB and MM.
Oh, here it is. Less 10% of the kinetic energy being transferred. TF is the energy of the fluid part.
Fluid part. Fluid part. Okay. Momentum of fluid part.
Can I proceed?
Yeah.
Okay. Now, the momentum of the fluid part is root 10 10v. Here we have assumed that momentum of the fluid is 1/100th of the melon and 1/100th of bullet. That makes it 1 2. Thus, the forward momentum of the fluid is greater than that of the bullet. Do you see that? Forward momentum of the bullet is here. 9. It is 3 times that. This is what causes the bullet to backwards. Incidentally, a toy model is being done with the ping pong bottles, and this person actually put some ping pong balls in it and let the ping pong ball move upwards. Then the thing which is holding it, which had some liquid nitrogen, it's moved upwards, and you can see this in this article. If you want, any of you want, I can share these articles. I can share it with Kagali or with Usha, and they will say. There is a much discussion of the assassination on Kennedy on 23rd November 1963. Let me make a personal comment here. I was attending a lecture as a student for PhD, and the news came at the lecture. The teacher just got up said, let's have 1 minute silence. And we had a 1 minute silence, and then we started the class. So that was something which was such a different cultural change for me going from India to the US. I learned a lot there because of this. For them, work was worship, and you have paid respect, and let's proceed. That's one of the positive points I learned there. Is there any question on this?
Thank you.
If anybody wants me to share this, I will share the entire all the files with Usha and Kali.
Yeah, you please share the entire files. Then we'll share it with the people who are interested. PDF file can be shared with us. So
is it all right if I just share it with both of you?
Yeah, certainly. We can pass it out to others.
But I need one more thing. After sharing it, please share the feedbacks that you get.
Certainly.
Collectively, we people can prepare a better document.
Sir, there is already a comment. We need this. Somebody is sent a message.
Where is
That
the
means
comment?
they would like to go through it and study it further. So
Happy to share.
we see a message here.
I don't see any message.
Chat, the chat box.
Chat.
Chat. Let me see where do I go to chat. Chat.
They want to have the file for leisurely study. Chat.
My chat is there. Let me see. Sir, we need this. I can see the message. You're chatting as a guest. Can post. I will certainly share it with Kagane and Usha. Is that adequate?
Yeah, certainly. We can pass it on to others.
But my only request is, please send your comments to them. Let us collectively make a better document. All right?
Yes.
Now, shall I proceed to the next one?
Please.
Okay, this will take a little longer. Maybe I will just go through. Let me just see what are the other ones I wanted to discuss. This is special theory of relativity taught in undergraduate?
Yes, certainly.
Okay, now this is the problem. This again, actually, I was a master's student in Delhi University when I thought of this problem, and I went to Professor Kothari. Professor Kothari, in his typical way, said, "You can't solve this? Do it. Think about it. I won't tell you the answer." Then I went there. I think I solved it. After a few days, I came back. He looked at me and said, "Acha, theek kiya tumne." So that was it. And I was very happy I solved this. The problem is this. I have a plane mirror with I've drawn PQ as the plane mirror, N is the normal, and a ray, incident ray AC hits the mirror, and the reflected ray OC goes. Then the mirror is at rest. Then the angle of incidence is equal to the angle of reflection. This is a standard Snell's law we learn in school. But what happens if the mirror was moving with some velocity v along PQ? I'm not making it move perpendicular. That also can be done. When I do that, it is very interesting. The angle of reflection is equal to angle of incidence. Though the actual values of the angle of incidence and actual reflection changes. And that's very easy to see. Because if the ray is moving, if the mirror is moving, there is no change in the perpendicular direction to the Lorentz transformations. So the perpendicular component of AC and BC, which are opposite to each other, will not go through any change. Whereas the parallel component are the same. So they will go identical changes. So there is no change at all in the relative momentum between the two. So the angle of incidence, though a different one from what it was earlier, is now going to be the angle of incidence, which is the new one. I will wait here for a minute.
Sir, we taught that when the mirror rotates through an angle theta, the reflected ray twice that angle. That is what we normally discuss, you know.
Yes, sir.
So how you are talking here is the angle of reflection and incidence remain the same even if the mirror is rotated.
Mirror is not rotating, it's just moving along the same direction. PQ.
No, I'm just making that. I'm taking a Lorentz transformation along PQ. I've just taken only a Lorentz. I'm not taking an arbitrary Lorentz transformation. For this, we can write down the full x prime equal to gamma, x minus vt, and so on. And these are four momentum. Four momentum are momentum and energy. Energy is the zeroth component or the fourth component, depending on the notation you use.
Yeah, if I understand, it's only Lorentz boost. Professor Mani is considering Lorentz boost,
Yes,
not,
no rotation.
not a general rotation. Right.
No, I didn't follow.
So the Lorentz contraction is anyway along the direction of motion, not along in the perpendicular direction.
No, the mirror is moving. The rays are not moving along with it.
No, but then the mirror has to move at the, close to velocity of light c, no?
No,
Otherwise, you don't see the relativistic effects.
See,
it can move with any velocity.
is that okay?
Yeah, it's okay. But we have to see the calculations.
Shall I proceed?
Yes.
This is a very, very interesting problem. Actually, we have built this apparatus in the lab. There is a ball A and another one C, which is marked red. The ball A goes on a horizontal plane. This is all vertical axis is gravity along the vertical direction. The ball A reaches B as I've shown. It takes some time to reach B. The ball C goes down the path F, E, G and it comes to D. Which one will reach the other side first, B or D?
My guess is both reach at the same time.
Pardon?
Same time.
Both reach at the same time.
No. C, the D will be first, then B.
Access to Chrome problem. So I think D.
No, B will be coming later. D will come first. It's a very good experiment to do in your lab. Let me just continue. I will just show you how. I will show you the diagram. The diagram is not there. Doesn't matter. Can you see my cursor?
Yes, we can.
Okay, now look at a point here. The ground, it's frictionless. We are not talking about friction. And the force is in this direction like this. So there is no horizontal force, V will remain constant. But let us look at this point. Here, the normal is in that direction. So there is an extra component. Just concentrate on the component in the horizontal direction. Vertical direction is going up and down, it's irrelevant. For we are interested in the time it takes to cross the horizontal distance. So take a point here and see where is it. It is there. So there is a normal force due to the ground in the horizontal direction. That means the horizontal velocity here will be larger than the corresponding horizontal velocity there. So this will cover this distance Fe earlier than the point here to this point. And in the opposite direction, though the force is this way, the velocity here is larger. The time it will take to go from F to E will be the same as it takes to EG. But the time it took to go from F to E was less than the time it took to go from that place to this place. So this will reach earlier. And we do this experiment in the lab. And when the school children come sometimes, they are totally amazed at this.
I just want to have a comment here.
Yeah,
That
please.
is, both A and C, initially they have constant velocity V in the forward direction. And in the end also they have a constant velocity.
Correct.
But one C undergoes a force in between, in the middle. The force which...
You're talking about this point?
Yeah. In
Okay.
between F and G, there is a force
No.
which is applied,
The
so that
normal reaction-
constant velocity has changed there. That is, that velocity which is...
But I'm not interested in the vertical velocity. I'm only interested in the horizontal component.
Fine. But initial velocity is V, final velocity is also V. In between, there is a force between points F and G, and one can check what is the horizontal velocity.
Yes.
So that will be larger. If it is shown, then...
No. So this will go in some time, and
Right.
this will go in
Agree.
time. It will,
Understand.
the lower one in red will go in less time.
Correct. Increase in velocity is what should be shown here in between F and G.
Correct.
Than the first one, when there is no force.
Is it all right? Do you
Yes,
want
thank
to
you.
again?
Thank
Yeah.
you.
Yeah, I have a doubt, sir.
Yes, go ahead, Malesh.
At E, it will have more horizontal velocity, right?
Correct.
But from E to G, it will have a normal force slightly towards the left.
Correct. But what is happening? When it reaches here, it should have the
Yeah.
same velocity as that.
But then my doubt is this
Here,
normal force, yeah.
the time it takes to come from F to E is the
Yes.
same as the time it took from E to G. Though it got slowed down here, but it was very fast initially.
I understood your explanation. My only remark is from E to G, will not the reaction force or
No, the
will
reaction
be
will be in this direction. As you point out, it will slow the ball down. But it will
okay, sir.
not be slower than the corresponding one here. Even then, the velocity here will be greater than V.
Okay, agreed, sir. Thank you.
Because it will be V here, so it has to be greater than V here to climb this.
Yes, sir. Yes, you can proceed, sir.
Is it clear?
Yes, yes.
Okay, good.
No, probably, sir. 1 second, sir.
Okay.
Please, no, I agree with our Mallesh, Dr. Mallesh. From
Yes.
E to G, it has to work against the gravity, no?
No, his point was, repeat it,
Sir,
Malesh.
you have to be a bit louder, sir. Sir.
Yes, Srikanth, please go ahead.
It works against the gravity.
Yes, Srikanta, can you please repeat what you said?
So
What
then
he's
naturally
saying,
its
see,
energy comes down, right?
Yeah. So what Malesh's point was, there is a normal in the opposite direction. So the ball will be slower than it was, which is correct. But the speed of this ball here is larger than V. So it will slow down till it becomes V. So in this path, its horizontal velocity is always greater than V.
Okay, sir. Okay.
Now I will not show you anything except that there is something called rattleback. I think many of you might have even seen it. This is a toy which is available in Amazon. I bought one here. You rotate it one way, it will rotate. If you rotate it the other way, it will just vibrate and stop. It will not rotate. So it is not symmetrical. The reason for this is that the mass distribution of this is not symmetrical, it is more on one side. How to do the calculation is a little long, and it is explained in a very beautiful book by Rajsekhar Velusamy and Sanjuan. It's available in Amazon, and I think you people should buy it for your library. There are many such problems there. Okay. Then there is one called the devil's stick. I used to own it, but I'm not able to see it here, and I will just show you. It was some kind of a rod in which you keep something like what children use for make aeroplane wings, two of them. When they run, the aeroplane wings moves around. But here, the rod is rectangular in shape and a uniform cross section. You go on rubbing one side, it will rotate clockwise. On the other hand, if you rub another side, it will rotate anti-clockwise. Again, the calculations are very difficult, and I have referred to a paper here, and it is given there. Now I will talk about one thing here. Why? The stability of a bicycle and how is it designed? Can I just, is it visible in the screen?
Yeah, we can see the figure. We can see.
Just draw a diagrammatic screen. Here, this is the front wheel, back wheel, and here is the joint, and this is the handle. and there is a joint which comes from here to here, and this is the seat. If you go and be in a cycle, you will see that this will go in the front. It will not go in the back like this. This is an unstable bicycle. This is a stable bicycle. I'm only talking about the stability in the longitude direction, not the transfers. The transfers involves angular momentum and so on. That has been studied in great detail. But I have not seen this in print anywhere. Now, the reason for this is, supposing I suddenly stop, the cycle will like to tend to break like that. But then this point, if it is here, when it's trying to move like the cycle moving like this, here the force, the thing will move that side, and this will try to give force in the opposite direction to keep it here. Look at it this way. Here, the cycle will move like this. This will also move this way. So this is unstable.
Very good.
I will not discuss this in detail. We are ending the time. I'll just make the last one. Cycle rickshaw. You know, all of you have seen cycle rickshaws. When a cycle rickshaw driver drives the cycle rickshaw automatically swerves to the left, does not swerve to the right. And the reason for that is the chain which is connecting the front wheel to the back wheel axle is not exactly at the middle, but at the side. So when he does that, when he pushes the thing here on the middle, when he pushes, he is exerting a force which is tending to move it in that direction. So he has to do it in the opposite direction. And there is no differential system in a cycle rickshaw because it costs money. In fact, in IIT Kanpur, they designed something which will help cycle rickshaw people. And I think this has been used there at great length. I think I'll just stop here for today. And thank you very much for giving me this opportunity. I hope whatever I've said can be communicated to the students in some form. Yeah.
Thank you very much, Professor Mani. Now it's time for some questions or comments. Anybody would like to ask any questions or make any comments, they're free to do so. Any questions or comments or suggestions, ideas?
Can I make a comment?
Please.
So this is regarding the Snell's law and Lorentz transformations.
Yes.
I just wanted to add a comment that if at all I had looked at what is degree of polarization, is it a Lorentz invariant? So
Oh,
that
very
was that was investigated, and it doesn't remain. If at all I look at polarization, and
okay.
I want to know the Stokes parameters and check the kind of invariants under Lorentz transformations, I would find that a elliptically polarized light remains elliptically polarized, but the volume of the ellipse would shrink under that. This is just a thing that was done in Mysore University long back, which is not published, but this is something in view of Lando and Lifshitz makes a footnote comment. Based on that, our teacher, Professor A.V. Gopal Rao, had done some calculations. I just wanted to mention it here.
It's fun doing the calculation. You're right.
Yeah.
Very good idea.
What happens to the law of refraction, sir, under the Lorentz transformation? Supposing you have a glass slab that is moving. What happens to the angle of refraction and incidence? What is the connection? Does it remain the same or does it change? Maybe it changes. So have you thought about it?
Really, no, I've not fully understood what you said. Can you please repeat
So
it?
the law of reflection, reflection you just mentioned that it remains the same.
Yeah.
What about the refractions? Refraction between two different media?
No, I've not thought about that.
Yeah. So because the velocities will be different in the two media.
Hello, Professor Mani.
Yes.
Am I audible? This is Sudha from Kuvempu University.
Okay, please ask.
Yeah. Am I audible?
Yes.
The problem in which the ball taking two paths one the linear path without having any force acting upon it, and the other in which it experiences a force in the middle, as shown in the
Which problem?
the
Two
problem.
balls A and C.
Parts A
There
and
is
B.
one is velocity which reaches fast.
Balls rolling, horizontal rolling.
Yeah, horizontal rolling, and the other experiencing.
Oh, horizontal rolling. So let's go there. 1 minute.
Yeah, that I think 10th problem also.
This one.
Yeah, this one.
Okay.
Here, like when you ask the question, which ball will reach first?
No.
One has to be like the force acting at E or F, I think. Yeah, the force acting at this point should be like one should know what is the force, so that the ball here too has the same velocity. Isn't that important for somebody who, for a student, initially it appears here that may, okay, after your explanation, one can see that the second one reaches first, but to do the calculation, etc., one needs to know what force should be applied. Am I right?
Let me just explain it. That is how crucial is velocity, initial velocity v and final velocity v
Yes.
for the
Yeah.
balls important.
Yes.
I didn't quite understand. Are you saying the difference in the arrival will depend upon V? That also most probably is right.
Yes.
And also when you do a
I
experiment
think it will be
for
lenient.
money,
If I change V to 2V,
yeah.
it will be
So,
lenient.
and when you do a experiment, Professor Mani, you
Yes.
should make sure that both the balls have same velocity. How do you do that?
Yes.
You mentioned that in CMI
No,
you do such an experiment.
You're right. We did that by using a spring, exactly similar spring on both sides.
Oh, okay.
And then we exchange the springs just to be sure that there's no error.
Okay.
Yeah. Thank you.
You're welcome.
Sir, with regard to the first problem, you said why there is difference between the calculated time and that. Yeah, that is what we normally say, that the sun is visible before it rises to the horizon. But how do we calculate it? Is it possible to calculate experimentally? Because how do we know that the variation of density from the surface of the earth to
We don't.
that position?
You have to model it. That's all. There's no way, as far as I know. You know, people, when they use rockets for defense, if an enemy aircraft is coming and they have to hit the aircraft by a rocket, these things are very important. Because the signals they get are optical signals, and speed of light is dependent on the refractive index. A small error means the rocket may not hit the enemy aircraft. So they model this by various ways. They send balloons up, and then they signals, and then they receive the signals. There are various ways in which this is done. It's a process which the military carry out very carefully at the border areas, I think. I do not know the more details. I've never looked at it.
Sir, I have one question. My name is Umesh.
Yes.
It is concerning the reflection problem.
Which problem do you want me to look at?
Reflection problem, sir. Reflection of light.
Reflection.
No, I didn't hear properly. Please repeat.
Mirror reflection. Reflection at a mirror. Moving mirror.
11.
Moving mirror reflection.
Yes. Oh, this one. No, this is a little more tricky. It will take a long time. You know,
My question was,
the last one, the bicycle stability.
Not this one.
The problem of reflection from a mirror.
Page 11, page 11, 11, page number 11.
This one, sir.
Page number 11, 11, 11.
11 is this.
Page number 11.
Page number 11.
Yeah, page number 11.
Okay.
That is page 9.
You are talking about this problem.
Yeah, that is the one.
So in this, the more detailed understanding of reflection is that you have atomic oscillators with which the light interacts, and then it coherently reflects in a direction OC. So is that interaction going to be of any importance in the?
So I think all that is taken care of in Snell's law.
But now we have, if we look at all the atoms aligned along the PQ line, those atoms will be moving.
PQ is the mirror. So I make the mirror move at constant velocity.
Yeah.
The molecules of the mirror move constant velocity.
Constant velocity.
Instead of making the mirror move, I move.
Yeah, fine. So that particular type of interaction which results in reflection, you say is included in Snell's law.
Yes.
But for reflection, do we talk about Snell's law? I think only with respect to the refraction we talk about Snell's law.
When we discuss Snell's law at school, we do not worry about the atomic structure. So now the question comes, why does light get reflected by a mirror at all? What happens? Why is it not absorbed? That's when molecular physics enters the picture.
Okay, sir.
That this will be discovered by, discussed by saying the molecules are excited to a higher level and then they get de-excited. There are several such molecules, and the coherent answer will be along the direction in which Snell's law holds.
Any other questions or comments?
Pardon?
I'm asking for any other questions, sir. If no other questions are there, I request our General Secretary, Professor Nagaraj, to propose a vote of thanks.
Yes, sir. In fact, you have thought of very nice problems. We normally take those problems simple, and we don't think of explaining how, even in respect of reflection or the calculated time, then when the ball is moving horizontally and another ball is moving slightly inclined, all those problems we take it for granted that we know. But anyway, you have raised many questions to think of, and definitely we think over all these problems which you have raised, and we will come back to you, sir. Thank you very much for sparing your time and giving food for us to think all these problems. Thank you very much, sir. I thank Dr. M.K. Raghavendra. He is providing the Zoom platform for our Zoom talk like this. And I thank Professor Usha Devi. She has introduced the speaker. And I thank the many invitees are there. I thought that even maybe from Tamil Nadu also some members who must have joined. I thank all of them. I thank all the members who have attended this session. I thank you each and everybody here. Thank you one and all. Thank you, sir. I think Professor Cogley has something to say about our next program.
We'll announce that. Probably we'll have some talk on the 19th. If nothing is happening on 19th, definitely we'll have it on the February 2nd. We have fixed a talk on February 2nd. Please attend. So now we are closing the meeting. I request Professor Mani to share his file with us so that we can distribute to our members.
Thank you very much. And I think if we can make this kind of document a little better,
We'll try. We'll add some more problems. We'll try to add some more problems.
Coordinate if it is possible. I know it will take times, but that's the way things work. Thank you once again.
Thank you, sir. Thank you.
So now we are
Thank you.
closing. We are leaving the meeting. Thank you very
Okay,
much.
fine, fine.
Thank you.
Thank you, Professor Mani.
Thank you, Malesh, for coming. I would like to chat with you whenever you're free. We should get to
Sure. We will be benefited. Thank you so much. Thank you so much.
Sure.